Welcome back, guys, once more. Now we will discuss all the advantages in graphing primal and dual problems. We are going to take a basic primal problem. From that particular problem, we just consider you guys, I'm going to consider actually, you guys used the previous video to find its dual form. And then I will plot its primal versus its dual and discuss on the solutions found. That is very informative. Consider you guys have this primal problem. Try to find its dual as an exercise. Just pause the video here. You guys probably noticed that this set of videos requires you guys to solve like some homework. That will probably take like a couple of hours to do. I mean, considering all the probably the last 3 videos plus this one, you're gonna take like some time to solve all those exercises. And then after finding its dual, just get back here, okay? And then look, compare to my dual and verify, of course, if it's right or not. Let's go. This is the dual. I'm just giving you, again, try to find it. Just consider something. My primal problem is in terms of 2 variables, x and y. And my dual is in terms of 2 different variables. This could be like lambda 1 and lambda 2, but here I just decided to call them as k and z. If my primal is a maximization, my dual is a minimization, and vice versa, of course. What I'm going to do now is I'm going to plot this and this problem. Both problems will work in different spaces of variables. That's something I want you to be sure about. Take a look at the graphs. First of all, let's start with the primal problem. We have x and y, and in this axis, we are going to have x. This y, of course. I'm here solving this first and the second constraints for the equality, both being equal to 2. Of course, the first constraint will be this one in blue, represented using blue points. As I need to be like smaller than or equal to 2, just take one point xy on this side and another on this side. You guys are going to be like, it's so easy to notice that of course my solution must satisfy as shown by this illustrative vector. This basically means, of course, that my solution is on this side of my constraint, my first constraint. The second constraint is here. Try to solve it for the equality equals 2, for x equals 0, and for y equals 0, and separate, of course. You guys will obtain this point 1, 0, and this point 0 minus 2. And this is my second constraint. My solution, it's not difficult to notice. Just plug some number on this side of this hyperplane and on the other side and verify which side satisfy the constraint. That's the side that's going to satisfy, which is illustrated here using this vector. So it's on this side. X has by definition, this is just the problem was given like this, x must be greater than equal or equal to 0 and y greater than or equal to 0. So I need to satisfy this second constraint, this first constraint, x must be greater than or equal to 0 and y greater than or equal to 0. Where is the region that satisfies all constraints? It's exactly this region. What happens if one of the constraints cannot be satisfied? For example, x has to be greater than or equal to 2. So x should be greater than or equal to 2. Is it possible to satisfy being on this side of this first constraint, on this side of this second constraint, and having y greater than or equal to 0 and x greater than or equal to 2? No, it's not possible. So this problem would never have a solution. However, x must only be greater than or equal to 0. So this is my feasible region in blue. Of course, it's an approximation. Sorry, guys, my bad. It's not like a perfect drawing over here, but that's what I do. Sorry. So this is one of the possible vertices providing a solution for me, for my problem. This is another. This is another 0, 0, and this is another 0, 2. Why I'm sure about those vertices? Again, my objective function is linear. It's going to be passing in a third dimension. If you guys just imagine a third dimension z coming out of this space, or any name you want to give it. Of course, if I project this region or this feasible region into my linear surface, one of those vertices will be related to a maximum or minimum for my problem. In my case, I want to maximize. If you try to solve this constraint equals to this constraint, you're gonna get this point, which is 4/3, 2/3. If I try to solve my objective function for 0, 2, for 1, 0, and for 0, 0, you guys will notice that the maximization happens actually here at 4/3, 2/3. This is the result 10.666 goes forever, okay, of my maximization problem. Of course, this is the solution for my objective function. If I apply 6 times 4/3 as x, 4 times 2/3. Try to apply here 4/3 plus 2/3. Is that smaller than or equal to 2? Yeah, of course. Because that will be like 6/3, and 6/3 is exactly 2. It's going to be equal. 2 times 4/3, that's going to be 8/3. Minus 2/3, that will be what? 6/3, and that's again equals 2. So, of course, my constraints are satisfied. X is greater than or equal to 0? Yes, it's 4/3. Y is greater than or equal to 0? Yeah, it is 2/3. And here I have my solution for this primal problem. When I go to its dual, take a look at the dual problem. I have another axis related to variable k, and here an axis related to variable z. That's a complete different space of variables. I'm going to go back. This is in terms of x and y. This is in terms of k and z. Those spaces are completely different, and I want you guys to be sure about that, okay? This is my dual. I want to plot this constraint and this second constraint. If I solve this for the equality 1k plus 2z greater than or equal to 6, try to solve for k equals 0. Z will be 3 for the equality, okay? So that's my point over here. And if I solve for z equals 0, my k will be exactly 6, which is in here, 6, 0, the other point. And this is my first constraint. Of course, I need to be greater than or equal to 6. And that lies on this side of my hyperplane. It's easy to notice that. Just plug like k equals 20 and z equals 20, which is a point over here. That will be greater than or equal to 6. That's why my illustrative vector points to this particular direction. What about the second constraint? If k0, z is going to be minus 4, as shown here. If z is 0, k will be 4, as shown in here. And this is my second constraint. I must be greater than or equal to 4. If I take any number here, like could be 4, 4, which would be a point over here. 4, 4, I would have 4 times k minus 4 times z, okay? And of course, that will be what? Take a look. Oh, sorry. Here would be minus 4, and here would be 4. So it's 4 in terms of k and minus 4 in terms of z. Sorry, my bad. So 4 in terms of k would be 4 times 1, that's 4. And minus 1 times minus 4, that would be plus 4. 4 plus 4 would be 8. 8 is greater than or equal to 4. So this side of this constraint has the solution and not this side, okay? So after drawing this, just find where we have still k greater than or equal to 0 and z greater than or equal to 0. So k has to be greater than or equal to 0 and z also. Where is my feasible set? It is here. Actually, it goes to infinity over here, okay, guys, in terms of k, sorry. That's my bad. In terms of my drawing, of course. Of course, it goes up as well in terms of z to infinity. Okay, that's my feasible region. How many vertices should I assess? How many candidate solutions? I have 6 and 0, and I have this as another vertex. Why those 2 points? Again, this is a linear optimization function. If I imagine the function being plotted in another third axis over here, the projection of those constraints will bring the solution to my problem. This is an important candidate solution, this is another. Okay, at this point, verify what is this vertex. It is exactly the point at which this constraint becomes equal to this second constraint, and that is 14/3 2/3. If I apply 14/3 as my k and 2/3 as my z, take a look what is the result of my minimization. That will be 10.666 as in my primal problem. What is interesting here that I want you guys to pay attention is my primal and my dual problems will have the same result in terms of their objective functions. So when I find the ideal kz, this objective function will be equal to, going back, to this objective function for its ideal x and ideal y. So when I solve my primal problem, my maximization for my primal problem, I will have the best value for x and y. And when I apply this objective function, of course satisfying the constraints, that's why we're drawing the constraints, that objective function will provide 10.666, okay, as seen, it is here, take a look again. And my dual will provide the same result for the best value of k and z. Again, take a look, 10.666. So what is interesting here is you can either solve your primal or your dual when it comes to linear optimization problems. You know what's interesting? I'm just going to give an additional step here and talk about some properties of primal and dual problems. If we are considering linear problems, just linear, don't think about non-linear. Linear optimization problems and their primal and dual forms, if I have a maximization of some objective function here and here a minimization of a different objective function, of course, those objective functions become eventually equal. We call that as a strong duality. What means strong duality? It means that if I have an ideal solution x star being applied here on this side, of course I have a corresponding lambda star that brings the best solution from the other side, and both objective functions will become equal, as shown before, as we've seen before. Okay? Just some important points here. If we're talking about nonlinear optimization problems, this is not ensured like for every nonlinear problem. No, it's not, unfortunately. For linear problems, we have the strong duality. This means that if I solve this primal, I will have the solution the same for the objective function for its dual, and vice versa. However, just the space changes, of course. Here it will be in terms of x, here it will be in terms of some vector lambda. Here vector x, here vector lambda. However, if we consider some nonlinear problem, sometimes there is a gap in between those two solutions. This gap means that besides trying to maximize this and trying to minimize this, even the best solution could have some gap, some distance in between them, some small distance. Could be a very small number, but that number might happen. We're going to discuss that later. Why we have here a less than or equal, smaller than or equal, operator? Because here I'm trying to maximize. If I'm trying to maximize, that means this objective function is smaller than or equal. Here I'm trying to minimize. It means that it is greater than or equal. So I'm trying from this side to minimize and from this side to maximize, and eventually they become equal. That's the point when I solve my linear optimization problem. Again, linear optimization problem. Please, guys, that's all for now. Just study that. I will recommend you guys to go to the book by Bazzara. I'm going to open here. Let's see. I have over here a set of slides that I just want to bring back to your mind. First of all, you can use the book by Moacir Antonelli Ponte and myself, Rodrigo Fernandes de Mello, of course. This book contains that subject, contains it like completely opened. Just download it. If you have access to Springer, to the website of Springer, if your institution provides access to this book, okay? If you don't have access, you can buy the book, of course. I'm just going to give you, of course, our library at the University of São Paulo has that book. Of course, this one by Moacir Ponte and myself, okay, Rodrigo Fernandes de Mello. Again, this book over here, let me show you guys. Where is the book? Where's the book? Where's the book? Ah, it's in here. Sorry, I'm just going to show like this. I think it's easier. This book by Bazzara and Jarvis and Shirali. This book has all that on linear optimization problems. Please try to get the book, read it. Read at least the points on linear optimization. That's going to be like 5 chapters, I think, like from the 1st to the 5th chapter. So that's part of this class. Please read it and bring your doubts to the office hours. Again, just getting back to the office hours, every Friday, actually it's wrong here, it's every Friday from 10, this is wrong, 10 to 12, 10 a.m. to 12. I sent you guys the link to the Google Meet, and we're going to meet over there, okay? And discuss more on this subject. See you guys in the next video.